Hello and welcome to the video lecture of Finite Element Analysis series. I am Bhavik Soneji and today I am going to talk about stiffness matrix. So let's get started. So in the previous video we have seen various concepts, key elements and various terminologies in the FEM. So let's understand what is a stiffness matrix. So as you know, the first step of the FEA procedure is to divide the whole problem into smaller finite elements. Like in this problem, you can see uh, this is the discretization of this body into different elements, and these different elements are connected by nodes or boundary or any surface. So the elements are different for different kind of problems. Like in the first case, if we are considering a structural problem, then we are applying some force here, and if we know the material property of this element, then we can determine how these nodes are going to vary or what are the changes in this node. So we can predict the behavior of element if we know the material property. For that, if we want to find out the deflection, we need some equations. So for each single element, there is a single equation, and for the combination of whole system, we will have to solve a set of equations. So to solve those kind of equations, we have two approaches. First is the force, or it is also known as flexibility method. Second approach is displacement approach, which is also known as stiffness method. So in both of these methods, we are focusing if the force is unknown. In that case, we are considering this method, and if the deflection or displacement is unknown, then we are considering this method. So in those two methods, from among these two methods, the formulation of equations from physical properties, the simpler method is this one. So we will opt for displacement method. Also it is known as stiffness method, and this is the today's topic, which is stiffness element matrix. So let's understand this method in detail now. So as I have said, for a single element, we have a single equation. For set of elements or whole system, we will have a set of equations. So to represent this set of equations, we have one representation scheme, that is matrix system or matrix notation. So various equations can be represented using matrix, and those can be easily solved because of in terms of they are matrix, it can be solved easily mathematically. So what we do is we convert these elements equations into matrix form, and that's why this method is known as stiffness element matrix method. So let's understand now what is stiffness element matrix or element stiffness matrix. So let's start understanding it by one example. So among the various problems like structural problem, or it is also solid mechanics, heat problem, heat transfer problem, then fluid flow problem, then electromagnetic problem. So among these, we will start uh, the simplest form of among these is the structural problem, in which we are considering a elastic material, and after that, after finding out the element stiffness matrix for elastic material, then we will develop a analogy for the other problems. So let's start. So we are considering a linear elastic spring element. So you can guess that what is linear elastic material? Elastic material means they are following the Hooke's law, and linearly they are following. So in that case also we have two things. Either it's a single element like this, there are two nodes of this single element, and in between these two nodes there is an element which is having some material property. Let's say it's a small k. Small k here represents the stiffness of the material. So in between these two points, in between these two ends or nodes, this is symbolic representation and it is denoted by k, which is a stiffness. We could have a combination or assembly of spring like this. So instead of a single element, we are having different elements. So the property will be different. For example, in between node number 1 and 2, there will be K1. For node number 2 and 3, K2. And between node number 1 and 3, K3. So the notation are here we are taking a small case K. There will be a different notation for a global matrix that I am going to explain in some time. So for here, for example, I am applying some force, then I will get a equation like this. So here these are the here the force will be equal to stiffness matrix into the displacement. So this will be the our formula here, and all the formulas are converted into matrix form. So here K will be the local coordinate system matrix and capital K will indicate the global stiffness matrix, and F indicates the force vector for local nodes, and U vector will indicate the local displacement vector. And if there is a assembly of spring, then we have to consider the global thing because they are having more than one element. So instead of vector, we have a matrix here, and instead of small k, there will be a capital K, and instead of small u, there will be a capital U. So there will be a global force, global force. Here will be the global displacement. So that's how we can convert one equation into matrix form. So let's understand it, how we can do that. So as I have mentioned earlier, there will be two coordinate systems. One is the local coordinate system and the second is the global coordinate system. So how to mm, note and how they are noted, or what are the notations of that system. So for example, this is my global coordinate system, like this is x direction, so x, this is y direction, and this is z direction. So this is my global coordinate system, and if I have some element like this, so it is also having two nodes. First node is here, second node is here. So this system, let me show it by other color so that it gets differentiated. And this direction is x direction. So here it is x naught, here it is small y naught, and here it is z naught. So the blue color indicates the local coordinate system, which is having three coordinates x naught, y naught, and z naught. And black color indicates global coordinate system. Which is indicated by small x, y, and z. So this is how the global coordinate system and the local coordinate system are having the difference between them. Now let's understand uh, how the equations come. So we will develop a relationship between the nodal force and the nodal element. So let's do it first. So this is the node number 1. This is my element, and this is node number 2. So total length of the node is capital L. Now this is just a symbolic representation of element. This element could have some thickness or it could have some cross section area. So instead we are only considering the deflection in one direction. So we are only representing it in one direction. So this is my direction in which we are representing it. suppose it is x direction. So now at this point the local force applied is F1, and due to some force the deflection of this node will be indicated by U1. Same for node number 2, the force is denoted by F2 and the displacement is denoted by U2. So now we want to establish the relation between the nodal force F and nodal element. These are the nodal. So here once again F1 and F2 are local nodal force, and U1 and small u2 are local nodal displacement. Now we want to establish a, a relation between these things. So let's say the element has the stiffness that is denoted by K. So now we can convert this thing, or now the K is nothing but the spring constant or stiffness constant, or it is also known as the stiffness of spring. Spring element here. So now we have given the notations, how they are notated. Now let's understand for different scenarios. If it is the scenario of a simple structural problem, then it can be considered for beam or circular bar cross sectional. For beam it can be any cross section area. For bar it's a circular cross section area. And for those problem, let us give the definition of K. So K will equal to, small k will be equal to capital AE divided by L, capital L, where A is the cross section area of the beam, E is the elastic limit or Young modulus of elasticity, L will be the total length of the element, so length of the beam here. If we consider bar here, then it will be bar under torsion. So that is also for same structural problem. So instead of capital A, here will be the J into capital G divided by L. J is nothing but the moment of torsional moment of inertia, and G is modulus of shear or shear modulus. Now considering the different problem, for heat problem heat mass transfer problem or heat transfer problem. K equal to small k equal to, instead of AE, here it will be A into Km divided by F, where Km is nothing but the heat conductivity. Same for if you are considering the fluid flow problem. For fluid flow problem, the notation will be same, but the Km meaning will be different. So here the Km will denote the permeability. So for different type of problems, same phenomena can be applied, but the meaning and the property will be changed. Like the property of material will be taken differently. So here, how you can note or how you can find the relation between the nodal forces and nodal displacement. So we have defined forces, local nodal forces, then we have defined local nodal displacement. We have defined K, that is material property. For different type of problems, they are different. Now we have to give the relation between these two. So how we can do? By combining this. Here the direction is x, so we are considering the vector. Force equal to stiffness matrix, that is K11, small k11, small k12, small k21 and small k22 into the displacement, that is u1 and u2. So here the k represent the kij. Here kij is nothing but the ith degree of freedom for or due to the unit displacement in jth degree of freedom. So here you can see the relation between the nodal forces and the nodal displacement, and here are the elements. So here we have defined the element stiffness matrix, and in the upcoming video we will see how to combine the local stiffness matrix into assembly and we can get the global stiffness matrix. So hope you find it useful. Thank you. See you next time.